Now, should have warned you all. Don't write any of that garbage. I'm going to like use up a whole pen's worth of ink taking that derivative. Yeah. So don't write for a second because I'm about to draw shapes. And when you look at your notes later, you're going to be like, what the heck? Okay. So I am going to do one thing, and I'm just going to like reminder whenever the power is right next to the trig function, that's the same as saying like that whole thing was cubed. Okay. So what if I just told you that that was like all of that garbage in there? I'm just going to call it box for a second, and it's cubed. So when I take the derivative of this, chain rule says I'm going to get this part you can participate with 3 times the box to what power? Totally. Times chain rule says I got to multiply by box prime. Yeah. Okay. So imagine I have some other terrible function. So I've got some other terrible function here. We still got box. Box is still our friend. All of that garbage in there. But I have 5 times that box to the 10th power plus 3 times his friend triangle, and triangle is going to be raised to the 4th power. So if I went to take this derivative, just think in chain rule, right? I got all that thing. That's what was shoved into my box. I don't know what terrible function is shoved into that triangle. But if I went to take this derivative, I'd end up with, yeah, box to the times, chain rule says, prime of the box. Then I'm going to get 12 times the triangle cubed times the prime of the triangle. One last one, and then I promise I'll stop drawing shapes. Let's say I had 5 box to the negative 3rd plus 7 triangle squared minus pentagon to the 1/2 power. And I went to take the derivative. I'm going to end up with negative 15 box to the totally times the prime of the box plus 2 times 7. That's 14 triangle to the 1st power, but that's going to look too much like a prime. I'm not going to write it. Times the prime of the triangle minus 1/2 pentagon to the negative 1/2 times the prime of the pentagon. Sweet. You all know how to do implicit differentiation now. But let's make it look like some of the problems in the actual book, because usually we don't have little cute shapes and stuff. Okay. So let's do something that looks a little bit more like calculus. And suppose that what I really had was this thing that looked like ugly function, I'll call it y to the 4th, plus other ugly function, we'll call it f. Let's make it 3f to the 5th. Another ugly function, let's make that h squared. How about another ugly function? Let's call it x to the 7th. One more ugly function, let's call it t. So I'll have like 3t to the negative 2. It's no different than if I had shapes up there. So if I go to take this derivative of y to the 4th, I'm going to end up with 4y cubed times the prime of y. 3f to the 5th, I've got 15f to the 4th times the prime of f. 6h squared, I'm looking at 12h to the 1st times the prime of h. 7x to the 6th times the prime of x. Negative 6t to the negative 3 times the prime of t. Now I gotta add on one little notation thing here. So sometimes when we write f prime, another way that we can write that is like df dx, or that y prime would be like dy dx. So h prime would be dh dx, and x prime would be dx dx, and t prime would be dt dx. So based on all of those, one of those 5 I didn't actually need to write. Which one of those 5 did I not actually need to write? Totally. Because anything over itself is equal to 1. Technically, we've been doing implicit differentiation the whole time we've been doing derivatives. It's just that that dx over dx term was equal to 1. But what if it was actually implied that all of these were functions of time, not functions of x? Well, that would mean that each of these derivatives is going to change. And if it's implied that all of these are actually functions of time, then that means we took the derivative of each of these with respect to time. Now, which one did I not need to write? Totally. Now, for some other thing, it might be implied that they're all functions of y, which would make this dy dy and df dy and dh dy and dx dy and dt dy. In which case, the one I wouldn't need to write is the dy dy. Most commonly, we're talking about a dt when we're thinking about related rates or things that are changing over time. And most commonly, we're talking about a dx when we're thinking about slopes or general derivatives of functions. So let's now get some stuff that you can actually put in your notes. Yeah? Would you believe me if I told you it's like a tilted ellipse? It kind of looks like this. Is that a function? How do you know it's not a function? Totally. So I've got, if I throw vertical lines on there, they're hitting the function twice. So it's not actually a function. But it's not like some crazy shape. I might still care about figuring out on this curve, what's the slope at a given point over here? I can't actually solve that to make it say y equals. But I still care about what the slope over here is. So the good news is that implicit differentiation is our way to figure out what the slope over there is, even though we can't make it say y equals. Because we still know that the slope has to come from a change in y over a change in x. So if they give us a particular point on this curve, oh, okay, I'm about to change the 12 because I can't do math in my head. Bear with me. I'm going to say that that's the point 2, 1, and we're going to make that a 9 instead of a 12. And I want to know, what's the slope of this curve at that point 2, 1? That's my objective. Well, if I'm going to find the slope, I need to take the derivative. And I'm going to treat this just like we did the previous problems, only I'm not going to draw boxes and triangles and stuff. I'm going to come through and just take the derivative of each piece. So my picture's kind of in the way here, so I'm giving myself a little bit more space. The derivative of x squared is 2x. And for completeness, I'm going to multiply by the prime of x. This next piece, that 2x times y, well, that I'm actually going to need a product rule for. Derivative of 2x is going to be 2x prime times y plus, leave the 2x alone, and for the derivative of y, I would get 1 times y prime. The derivative of y squared is 2y times a y prime, and the derivative of 9 is 0. Just like on that previous problem, these x primes would be a dx dx. So I don't have to write those. The y primes, on the other hand, I do have to write because things do not magically cancel out there. So if I clean this up and only keep the parts that I really needed, this is going to look like 2x plus 2y plus 2xy prime plus 2y y prime is equal to 0. Now to get my slope, I'm looking for that y prime term. We actually have a choice to make right now. We could just plug the point in first and then rearrange for y prime, but there are going to be some problems where we have to get the y prime by itself before plugging numbers in. So we might as well get the practice with that now. In order to solve for that y prime and get it by itself, I want to get the two pieces that have y primes on one side and the two pieces that I've got here without y primes, shove them to the other side of the equation. So I'm going to subtract the 2x and I'm going to subtract the 2y. Over here, since these two terms have a 2 and a y prime in common, I'm going to factor out that 2 and the y prime. From the first piece, that'll leave me with an x, and from the second piece, that'll leave me with a y. Not sure if that was a question. Someone unmuted themselves. I didn't catch it if it was a question. I'll assume it was an accident. Throw something in the chat if it wasn't. Okay. So to get that y prime by itself now, I have to divide by everything. So I've got negative 2x minus 2y, all divided by 2 times x plus y. And to get the slope at the point I actually care about it, now I'm ready to plug in the x and y values. So the slope, when I care about it, x will be 2 and y will be 1. So on the top, I've got a negative 4 minus a 2, and on the bottom, I've got 2 times 2 plus 1. That's a negative 6 over 6. Cool. Slope is negative 1. I didn't even do too bad on the picture. And someone in office hours asked me, like, if it doesn't say to use implicit differentiation, how do you know that you have to? If you look at the equation and you can really easily rearrange it to say y equals, then you should just do that and then take the derivative normally. But if you look at the equation and you're like, well, dang, I don't even know how to get a y out of a sign, we're stuck. We're going to have to do this implicitly. The derivative of sine of 3y, kind of that outside function is sine. So I'm going to end up with cosine. Calculus can never change what's inside. But now the chain rule says I need to multiply by the derivative of 3y, which is going to give me a 3 times y prime. Or if you want, you can just go ahead and write that y prime as dy dx. For me, the primes just look so much, it's like for me personally, the prime looks so much like I've written something raised to the first power that I prefer to write dy dx. I know it gets a little bit messier, but it's ultimately in my best interest to write it that way. Derivative of x cubed, I'm going to get 3x squared. I would write dx dx, but I know that I'm doing it with respect to x, so I'm not going to worry about that. It would just be equal to 1. Derivative of 2y, I'm going to end up with 2y dy dx, and the derivative of 2x is going to be 2. Because here I'm looking for dy dx, I kind of have to sift through all the garbage and say, okay, I've got 2 terms with dy dx in them. I need those on the same side of the equal sign and everything else on the other side. So I'll have cosine 3y. I'm going to put that 3 over here just so I don't get confused. Minus 2y dy dx is equal to 2 plus 3x squared. Next, now that it's all together, I can factor that dy dx out. I'm going to do 2 algebra steps at once. So imagine I factored it out, and then after I factored it, I'm going to have to divide everything back over. So I'll have dy dx is equal to 2 plus 3x squared over everything I factored out. So 3 cosine 3y minus 2y. And then we quit and walk away. Have choices. One choice that we can make, because we're going to do this implicitly anyway, we can rearrange this stuff right now if we want to. Meaning I could choose to multiply both sides by x minus y before taking the derivative. And that's probably what I would choose to do with that fraction. Now, it's going to give me more product rule doing that, but at least I won't have a quotient rule. So I don't know. Does anyone have a preference? Multiply stuff or just use the quotient rule? No one seems to have a preference. Let's just use the quotient rule because it's already looking like a fraction. Good times. So I'm thinking about everything on top as an F and everything on the bottom as a G over here on the left-hand side. But when I take the derivative of the top, there's a product rule just for fun. So the derivative of that top there is going to look like 2x times y plus x squared times dy dx. And that whole thing was just to get the derivative of the top. Now that'll be multiplied by the bottom minus, leaving the top alone, times the derivative of the bottom. And we do want to be careful when we take the derivative of the bottom. The derivative of x is 1. So I'm going to get 1 minus dy dx. That whole thing is over the bottom, sorry, it's minus y squared. And then we can take the derivative of the right-hand side, and I get 9x squared. Whatever else is going on, I know that my objective is to get these dy dx pieces by themselves. There is a whole lot of algebra between me and that. Okay, my internet connection is getting worse. So Let's see what we can do. And if I get disconnected from Zoom, I promise I'll be right back. Dun, dun, dun. Okay. Don't know if that got any better. We'll see. So algebra wise, I'm going to multiply both sides by the denominator now. I'm not going to bother distributing that out. I am going to look at the top here. I've got 2xy plus x squared dy dx. That's still times an x minus y. Minus, I'm going to go ahead and distribute this out. So minus x squared y plus x squared y dy dx is equal to 9x squared times x minus y squared. If my objective is to get the dx dy's by themselves, I don't really have a choice. I have to FOIL this out, or at least distribute the x minus y through. Whether you like completely multiply stuff out or just drag around parentheses, either one's fine. So I'm just going to drag around the parentheses and say this is 2xy times x minus y plus x squared times x minus y times dy dx. This little piece right here is kind of in my way anyway, so I'm going to add it to the other side. Again, these are the parts I'm trying to get by themselves. I'm going to subtract this whole thing over, factor out my dy dx, divide by the stuff that's left. Can I do those three things at once? Maybe. Let's see. Okay. Maybe I'll do, I'm going to do two steps. So I'm going to factor out the dy dx. So I'll have x squared x minus y plus x squared y. And on the other side, I've got 9x squared times x minus y whole thing squared plus x squared y, and then I'm subtracting off the 2xy times x minus y. And my last step would be to divide by this thing. Good times. This is probably as gross as it gets. I mean, I know it might feel more gross if I threw extra trig in there or something, but really, this is about as gross as the algebra is going to get. Yeah, there are all kinds of things you could do to manipulate that or try to simplify it, but it's not really ever going to get a lot better.